Welcome to all of you in this video. Myself Sumit Kaur from Impulse Technology. In this video, we will demonstrate adsorption energy in bulk PD material. So now we have to start this video. So we'll go to the our software, that is Device Studio. So you can see this is the device user interface in which you can create a new project, or if you have some existing project, you can directly locate that file and that will be open. So I will save this project with name PD. So I will click enter, and as you can all see, this is our device studio user interface, in which we will first try to make the structure of PD material. Uh, then we will try to find their total energy. Then after we will try to demonstrate and try to calculate the energy of total energy of that particular material. And after that we will calculate their adsorption energy. So first we have to make the structure of PD, in which their orientation will be 100. So first we have to go on build option and click. So first we have to go on file and click new and click crystal, and after it we'll have to take the parameters. So in crystal, I will put the value of A, B, C, and alpha, beta, gamma. And this is the previously lattice, that is the triclinic. And I was selected PD, in which I put it their fractional coordinates and as well as and click preview. So this is my PD bulk material I have, which have the orientation of 100. So click build. Now we have to, if someone wanted to do the structure relaxation, so they can directly do with NanoDcal relax, and when you click the relax, and they can do this like they can give their electron temperature, energy cutoff, exchange calibration value, and K point sampling as well. And also relax. In when we go to the relax, there is a MD and CD type, that is conjugate gradient, and they can give their energy a force convergence criterion, and after they can select their station control and their basic sets and their spin type, if there is something spin type of arrangement, that is collinear or general, they can select it. Now we only do the we have to only find the total energy, so we'll go to the simulator and NanoDcal and SCF calculation. As you can all know, in SCF calculation, you can give their electron temperature, energy cutoffs, exchange correlations, and K point sampling. As you all know, in SCF calculation and relaxation, there is one tab is there is a one more options are shown, that is the relax. Either other parameters are same. So we'll set the values like 9, 9, and this will be also 9. So, and if you want to change the iteration control, their mix rate, and if someone wanted to give the energy to this crystal, so they can give, and in the basic set, they can select their arrangement, their Hubbard terms, and their spin type values, and spin type values like collinear general, and they can click generate file. When we click the generate files and there is a scf.input files is created. Now we have to open with. So now we have to do this see, this is the scf.input file for this structure, and there in this you can see that this is the electron temperature, their energy cutoffs, their exchange correlation functions, and their k point sampling values. And if you wanted to see the total number of atom blocks, that is 4, and all types of input that is written in scripted form. So now we have to run it. Click run. Now you can clearly see the job status is shown here. So now let it be running. And if you want to see the status of your calculation, you have to simply that there is a log.txt file. It shows the status of your calculations. So in you can as you can see, your calculation is running. Now this is the job manager where you can also see the status and see this is calculation is running for. Now we have to take the another since uh, we wanted to find the adsorption energy. So first we have to uh, merge or some we have to bond some another material into this crystal. So we'll go to the build option and we will try to make another type of structure. So in which I will add some crystal add some atoms into this crystal. So I have to take the same atom and put the values. So now, as you can all see, I put it the same PD values and another we will take the another oxygen and C, O and C type of element, and these are the previous lattice in which I put it the ABC value, alpha, beta, gamma value, which are 90 degree. That means this is a orthorhombic structure, and I will give this parameter. I will click on preview. When I click the preview, you can see this is the structure. We will ready it. Now we have to click on build. So after the build, you can see this is our structure. Now we have to find the adsorption energy. So let it be okay. So now we have to calculate the SCF calculation. So go to the NanoDcal and SCF calculations, and there is a spin type which you can select. There is spin type like general and collinear and type spin, and we'll set the basic sets. Now we have to. I will select the 9, and this will be also 9. And if you wanted to give the electron temperature, you can take it from here. Energy cutoff, exchange correlation value, iteration control, in which you can change their mixed rate, basis rate, in which you can set their Hubbard term or spin type, general or collinear, you can select it. Now we have to click on generate file and click scf dot input file. And if you wanted to see the input file in script form, you can see from here. If you wanted to change something, you can directly change from here and save it. Now that will be saved. Now you can see the temperature, uh, energy cutoff, exchange correlation value, and K point, and their mix rate. And you can see here no spin is selected. That means there is a no spin. And these are the atoms which are selected for the different exchange correlation function with different values. And these are the atom block. That is we have a total number of 6 atoms. So now we have to run it. Simply click on run, and so in which you can see the result. If you wanted to see the status of your calculation, there is a job manager, as you all know, and this is the status that is running and the process. If you want to see the status, you can simply click on I button, and as you can all see, the calculation is running. Okay, now after this, we have to uh, take the another one. I will take the PD atom. So I will go to the file, click new, and click import. Import online. I will click on PD and search it. Now I will select this PD1 atom. So I will click on this and I will set the go to the 3D viewer in which you can select their you can change their view. So I will select the XY view. Now I have to calculate. So go to the simulator and NanoDcal SCF calculation. So in SCF calculation you can set their values and their exchange correlation value, their energy cutoff, their electron temperature, their attrition control, their basic set, their spin type, whatever you need, you can change it. Now I will click on generate file. Now let it be not done. For now we will try to calculate the relaxation. So I will delete it. Okay. And now I will try to get the relaxed output for this PD atom. So I will go to the simulator option, NanoDcal, and click relax. When we click relax, you can see this is the relax output is selected. Now this is the basic setting. In electron temperature, energy cutoff, exchange correlation, K point sampling, I will select it 9, 9 and 9 and relax. I will select, you can select the MD or GCG, that is conjugate gradient and the iteration control, their basic set, their spin type value. Simply you can select them all and generate file. When you click the generate file, in the and the another type side, you can see when we click the scf dot input file, when we create the scf dot input file, this is the scf dot input file. When we click the relax, we will get the relax dot input file. So we'll try to relax it. So simply run it, and as you can all see, our nanodecal.scf.input file for the this crystal is now ready. Calculation is completed, and for this relax.input file, I wanted to see the status of our calculation. So log.txt file and open with, and as you can all see, our calculation is running. Okay, now we wanted to see the energy of this. We wanted to calculate the energy of this material. So I will go to the simulator. Now we have to first calculate the energy of for this. So go to the simulator and click NanoDecal, and there is an option called analysis, and there is a total energy. I will select it and click generate file, and for this crystal I will select the total energy. So analysis, and I will select the total energy. So as well as for this PD atom, so nanodical analysis and total energy. So as you can all see, the relaxation input, after the relaxation, there is a one file will be generated like atoms slash relax.xyz. Okay, this is the output file. You can select open with, and this is, you can see, this is output for this relaxation. Whenever you do the optimization of any type of crystal material structure, after the if you wanted to know your calculation is completed or not, you can see whenever until you are not getting the atom slash relax dot xyz file, that means your optimization is not completed. So you have to patience because in relaxations output, when you calculate the relaxation or optimization, it will take some time because it's have a some there is a lot of calculations are happening in this type of calculation. So in our scenario, I have only one atom, so the calculation is completed very shortly. When we have a number of calculation, like if you will calculate it like this type of structure for the optimizations, or for this type of structure we do the relaxation, will face some time like about to 5 to 8 or 8 to 10 hours. So you have to take the patience when you optimize the calculation. But I wanted to introduce some a new feature which is uh, updated in our new software, that is 2024. When you click on simulator option, there is a AI relaxation. I will demonstrate some calculations, and I will demonstrate some uh, tutorials on it after this. So this will take the lesser time for the relaxation output. So now you can see now we have to run the total energy. So run it. First I have to run this one. So click it. Now I have to run the total energy. Run for this crystal also. Try run it for this PD also. Run it. Now as you can all see, our total energy for this first crystal is running condition, and this is also completed, and another one is running, and the third one is in Q form. After the running the calculation, we will see the result into the MATLAB. Now our all calculations are calculated for the SCF dot input file as well as total energy. So you can all see. Uh, Now we will try to get the raw data of output for total energy in MATLAB. So we'll go to the MATLAB, like we have open, and locate that file directory. You can see I already located it. Like my file is already saved here with name PD. So locate this file directory, and as you can all see, now we have to take the total energy data. So before the showing it, I wanted to see the total energy dot mat file. This is the this for the PD term. So PD bulk material. So I will click on I load it and type data. See, this is the this total energy for the single PD atom. Now we have to take the data. We have to find the data of bulk material of PD. So I'll go to the load for this crystal and type data. Now this is the total energy of PD with carbon monoxide, and for this is the bulk material carbon with 100 orientation. Now load their mat file of total energy and type data. So these are the values of total energy. Now for the calculation calculated this value for the absorption of the value. Uh, Now we have to go on So for so for for absorption energy, we have to find the total energy. So we have calculated the total energy of that materials, and the formula for finding the absorption energy. This is the delta E is equal to uh, adsorption the material having the absorption, that is our PD 100, that is the bulk material, and having the absorption of carbon monoxide, and minus total energy of bulk material PD, and a single total energy of single PD material. So as you all know, we have calculated this total energy value and put this value into this equation. And after the putting the equation, we will get this value of total energy in Hat3 0.0917 Hat3. After doing this, after converting into Hat3 into the electron volt, you will get the 2.9495, about approx 2 point minus 2.5 electron volt energy. So this is the adsorption energy. You By that method you can calculate it. So thank you for everyone to watching this